Okay, today our topic characteristics parameters of JFET. So last class we seen about FET, introduction to FET. In FET we studied different types of categories. So FET is a field effect transistors. It is divided into two types. One is JFET, other one is MOSFET. So JFET again divided into two types. One is N-channel JFET and P-channel JFET. And what is MOSFET? MOSFET is a metal oxide semiconductor FET. It is divided. It is also called as IGFET or MOST. IGFET means insulated gate metal oxide semiconductor FET, and MOST means metal oxide silicon transistor. So the main difference between BJT and FET is, so FET is a voltage control device and BJT is a current control device. So in the operation point of view, we will see uh, both are similar, except in fact there is a field effect instead of majority and minority charge carriers. Okay. So FET symbol we also seen. FET is a three-terminal device. BJT is also three-terminal device. So namely, in fact, gate, drain, and source. Okay. So today we will see some characteristics parameters of FET. So we have seen in FET three terminals. So 3 volt, two voltages are exist. One is VDS. VDS means drain voltage from drain to source, and VGS, that is gate voltage from gate to source, and also drain current is also there. So here among three terminals, we have to fix one among three uh, parameters. We have to fix one parameter so that we can find the relationship between two parameters. For example, if you fix VGS is equal to some fixed value, we have to find the relationship between ID and VDS. Similarly, we have to fix VDS is equal to some fixed value. We have to find the relationship between VGS and ID. Likewise, we have to fix one parameters and find the relationship between other two parameters. So in JFET, the drain current ID depends upon the drain voltage VDS and gate voltage VGS. Okay. Any one of the variable may be fixed and the relationship between other two variables are determined. So we can find three parameters here. One is transconductance or mutual conductance. It is denoted by GM. So GM is equal to dou ID by dou VGS. This one is dou ID by dou VGS at constant of VDS, because here VDS is the fixed value. We can find the relationship between ID versus VGS. So change in ID by change in VGS at constant VDS. So this is called transconductance. We know that what do you mean? V is equal to IR. We know the basic formula. R is equal to V by I. So this is called resistance. Inverse of resistance, we call it as conductance. So here we call it as transconductance. The units of transconductance is mho. So mho symbol is like this. The unit of transconductance is mho. Okay. Next parameter is drain resistance. So drain resistance is the reciprocal of the slope of the drain characteristics and is defined as RD is equal to dou VDS by dou ID at constant VGS. That means a small change in VDS to corresponding small change in ID whenever VGS is equal to constant. So here also three parameters we have here. VGS is constant. Okay, the units of resistance is ohm. Okay, the units of resistance is ohm. Next, we will see some other parameter here, amplification factor. So amplification factor mu is equal to minus dou VDS by dou VGS. Dou VDS by dou VGS at constant ID. At constant ID, we call it as amplification factor. Okay, here the negative sign shows that when VGS is increased, VDS must be decreased for ID remains constant. For ID remains constant. Okay. So relationship between among FET parameters are, we know that three parameters. One is ID, this one is ID, VDS and VGS. So the functional equation can be expressed as ID is equal to function of VDS comma VGS. So drain current, ID means drain current is equal to function of drain voltage and gate voltage. So this is the relationship among FET parameters. These are three parameters. So ID is a function of drain voltage comma gate voltage. Drain voltage comma gate voltage. Okay. So the drain voltage is changed by a small amount. Drain voltage is nothing but VDS. It is changed from small amount. Like we can say delta VDS, and similarly gate voltage is changed by a small amount from VGS to VGS plus delta VGS. Then the corresponding small change in ID, may be obtained by the Taylor's theorem. So what do you mean by Taylor's theorem? We have to eliminate the higher order terms here. So now we are changing drain voltage from VDS to change in VDS. Similarly, gate voltage is changed by a small amount from VGS to change in VGS. At the same time, ID is also changes. Thus, the small change in ID can be written as by using Taylor's series. So change in ID is equal to dou ID by dou VDS at constant VGS into change in VDS plus dou ID by dou VGS at constant VDS into change in VGS. So this denominator term VGS and this term is similar. Here also denominator term dou VDS and change in VDS both are same. So dividing the both sides of the equation by VGS, change in VGS, we obtain by dividing change in VGS means we have change in ID current. ID current means drain current. So change in ID by change in VGS is equal to, this term is similar, change in ID by change in VDS at constant VGS into change in VDS drain voltage by change in gate voltage here plus change in drain current by change in gate voltage at constant VDS. So here ID is a constant. So the differentiation of or partial differentiation of constant is nothing but 0. So 0 is equal to dou ID by dou VDS at VGS constant into same term, this term, and change in VDS by change in VGS, this term as it is, plus change in ID by change in VGS at constant VDS. See, we know that change in ID by change in VDS. We know that just now we seen that is called drain resistance. So the reciprocal of change in drain resistance is nothing but transconductance here. So dou ID by dou VDS is 1 by RD. So dou VDS by dou RD is nothing but drain resistance. Here it is inverse. So the reciprocal of dou ID by dou VDS is nothing but 1 by RD here. And the change in drain voltage by change in gate voltage is nothing but amplification factor. Just now we seen at constant drain current plus, what do you mean by change in drain current by change in gate voltage at constant drain voltage is nothing but transconductance. Okay, so from this equation we will write it as Gm is equal to mu by Rd. So Gm is nothing but transconductance, mu is the amplification factor, and Rd is nothing but drain resistance. Okay, from this equation we can write it as mu is equal to drain resistance into transconductance. So therefore, the amplification factor mu is the product of drain resistance and transconductance. So mu is equal to Rd into Gm. So we will see the related problems. When a reverse gate voltage, what do you mean by reverse gate voltage VGS of 12 volts is applied to the JFET in junction FET. So reverse voltage VGS is applied to the JFET. The gate current is 1 nanoampere. So determine the resistance between the gate and source. That means resistance between the G and S, gate and source. So first of all, whenever problem is given, we have to write the given data. So here given data is reverse gate voltage. That means VGS is given. So it is at 12 volts, and other parameter is gate current. IZ is given. So IZ is 1 nanoamperes. So VGS is equal to 12 volts and IZ is equal to 1 nanoamperes. Nano means 10 power minus 9. So therefore the gate to source resistance is gate voltage by gate current, that is called gate to source resistance. We will get 1200 mega ohms. Similarly, when a reverse gate voltage of JFET changes from 4 to 3.9 volts, the drain current changes from 1.3 to 1.6 milliamperes. Find the value of transconductance. We know the formula transconductance Gm is equal to change in ID by change in VGS. So here gate voltage changes from 4 to 3.9. That means the difference 4 to 3.9 is 0.1. That is called change in gate voltage. Similarly, the drain current changes from 1.3 to 1.6 milliamperes. The change is 1.6 minus 1.3. That means 0.3 milliamperes. That is change in ID. So transconductance is equal to change in ID by change in VGS. That is change in drain current by change in gate voltage. We will get three moles. So transconductance units is moles. So resistance units is ohm. So this is the inverse. The reciprocal of resistance is nothing but transconductance. Now we will see the expression for saturation drain current or transfer characteristics of junction FET. For transfer characteristics of gate voltage or drain voltage, we will see here. So the drain voltage maintained at a constant at a suitable value greater than the pinch off value. So previous class we seen what do you mean by pinch off value. So whenever drain to source voltage is increased, at some point of time both gate terminals are close together in reverse bias. So whenever close together means there is no channel appears in the middle. So that both contacts, both terminals are contact to each other. At that time, there is no gap or no channel. That point we call it as pinch off value. Corresponding voltage we call it as pinch off voltage, that is VDS. So the gate voltage is decreased from 0 till ID is reduced to 0. Here you can observe. So this y-axis is ID, means drain current, and x-axis is VGS, means gate voltage. So the gate voltage is decreased from, this is the origin. The gate voltage is decreased from 0 till ID is reduced to 0. See, you can observe this curve is a parabola structure. Here ID, drain current is reduced. Drain current is reduced whenever VGS is increased up to drain current reaches to 0 whenever that voltage is, we call it as pinch off voltage. So this is called as transfer characteristics. If VGS is equal to 0, drain current is maximum, that current we call it as IDSS. That current we call it as saturation drain current. IDSS means saturation drain current. So in transfer characteristics, the shape is nearly look like parabola. So the parabola equation can be represented by IDS is equal to IDSS into 1 minus VGS by VP whole square. So where IDS is equal to saturation drain current, IDSS is equal to the value of IDS when VGS is equal to 0. So just is seen here. See, the value of ID is the maximum when VGS is equal to 0. So this is the VGS is equal to 0 point. So ID current is maximum. That maximum current we call it as IDSS. That means the value of IDS when VGS is equal to 0. IDSS means. Here VP is equal to pinch off voltage. So differentiating with respect to VGS, we can obtain for the expression for GM. So change in IDS by change in VGS is equal to, what is the differentiation here? X square means 2x. Similarly, here IDSS into 2 into 1 minus VGS into the coefficient is with respect to VGS means we will get minus 1 by VP. Okay, we know that GM transconductance is equal to dou IDS by dou VGS at constant drain voltage. Therefore, GM is equal to minus 2 IDSS by VP into 1 minus VGS by VP. So from the above equation, we can write it as 1 minus VGS by VP is equal to, so it is a square term, 1 minus VGS by VP is equal to IDS by IDSS. So substituting this equation, this into equation 2, we will get GM is equal to minus 2 square root of IDS into IDSS by VP. VP means here pinch off voltage. So what do you here, suppose when VGS is equal to 0, VGS means gate voltage. Gate voltage is equal to 0. Transconductance is nothing but GMO, that is transconductance. So GMO is nothing but minus 2 into IDSS by VP. So from the equation 4, we can write it as GM is equal to GMO into 1 minus VGS by VP. So the slope of the transfer characteristics IDSS can be written as GM is equal to minus root of IDS into IDSS or by VP, or change in IDS. GM is nothing but change in IDS by change in VGS is equal to minus 2 into root of IDS into IDSS. So substituting this IDS is equal to IDSS. So what do you mean by IDS and IDSS? So IDS is nothing but charge S for saturation drain current. ID for drain current, S for saturation drain current. IDS is nothing but saturation drain current. IDSS is nothing but the value of IDS when VGS is equal to 0. So when VGS is equal to 0, the maximum drain current, we call it as IDSS. Okay, from this equation, we can tell you that ID is equal to IDSS into 1 minus VGS by VGS off. So we will see the related problem here. The FET has a drain current of 4 milliamperes. If IDS, you have to whenever problem is given, first you have to write down the given data. So here given data is the drain current of 4 milliamperes. Drain current is denoted by ID. So ID is equal to 4 milliamperes. If IDSS is equal to 8 milliamperes and VGS off is equal to 6 volts. Find the values of VGS and VP. So we know that ID is equal to IDSS into 1 minus VGS by VGS of whole square. So given that, substitute here, ID is equal to 4 milliamperes, IDSS is equal to 8 milliamperes. So here unknown term is VGS. So that is gate voltage. So from these equations, we calculate VGS is equal to 1 minus 1.76 volts. So what do you mean by VP? VP is equal to modulus VGS off. That means it is 6 volts. Next, an N-channel JFET has IDSS is equal to 8 milliamperes and VP is equal to minus 5 volts. So this is another type of problem. So determine the minimum value of VDS for pinch-off region and the drain current IDS for VGS is equal to minus 2 volts in the pinch-off region. So the minimum value of VDS for pinch-off to occur for VGS is equal to minus 2 volts is given. So write down this. So VDS minimum is equal to VGS minus VP. So substitute these values. VGS is equal to minus 2 minus 5. We will get 3 volts. So IDS is equal to IDSS into 1 minus VGS by VP whole square. So IDS is equal to 8 into 10 power minus 3 into 1 minus, what do you mean by VGS here? VGS is equal to minus 2 volts by VP is equal to, just now we find VP is equal to minus 5 volts. So substitute all these values, we will get 2.88 milliamperes. Okay. Okay, let us summarize today's session. Today we will see characteristic parameters of junction FET. So characteristic parameters is nothing but in junction FET we have three parameters. One is drain current, gate voltage, and drain voltage. We have three parameters means we have to fix one parameter and find the relationship between among two parameters. For example, I fixed ID is equal to some fixed value. So what are the remaining parameters? Remaining parameters are gate voltage and drain voltage. We know there is a relationship between gate voltage and drain voltage is nothing but amplification factor. Likewise, we see three parameters. One is transconductance or mutual conductance. So that is denoted by GM. So GM is equal to dou ID by dou VGS. That means change in ID by change in VGS. Change in ID by change in VGS at constant VDS. So the units of transconductance is nothing but mho. So it is a reciprocal of resistance. Transconductance is nothing but reciprocal of resistance. So next parameter is drain resistance. Drain resistance is nothing but change in VDS by change in ID. Change in VDS by change in ID at constant VGS. Similarly, amplification factor. In amplification factor, which term is constant? ID is constant. That means drain current is constant. Remaining parameters are VGS and VDS. So change in VDS by change in VDS at constant ID, we call it as amplification factor. And also we will see in the relationship between FET parameters. That means gate drain current is a function of gate voltage and drain voltage. This is the relationship between FET parameters. So ID is equal to function of VDS comma VGS. And also we see the relationship between transconductance, amplification factor, and drain resistance. So the relationship between these parameters GM is equal to mu by RT. So mu from that mu is equal to RD into GM. Okay, that means the amplification factor is the product of drain resistance and transconductance. And we will see the relative problems, and then we'll see the transfer characteristics of JFET. So transfer characteristics means VDS is maintained constant at a suitable value greater than the pinch off value. Okay. Here in x-axis we are taken VGS and y-axis we are taken ID. So when VGS is decreased from 0, that means -1, -2, -3, ID current is also decreasing from maximum IDS saturation current to the 0. Whenever ID is 0, that voltage, corresponding voltage VGS, we call it as pinch off voltage. And also find the relationship between ID and IDSS. So here ID is equal to IDSS into 1 minus VGS by VGS of whole square, and find the this transfer characteristics. Okay, and also we see in the related problems, transfer characteristics problem. Okay. Okay, thank you.